So hello everyone again. So in this chapter of the video, I would like to share with you about more insights into the principles behind the control moment gyroscope and to share with you the features behind it and what kind of advantage that people can have while using the CMGs inside their ADCS system. So firstly, we can look into an interesting dimensional analysis about satellites. If you picture the satellite into a cubic shape like this, and then we put its dimension to be d, then people can usually be able to find an interesting fact about it is that the volume of these satellites is usually proportional to the d to the power of 3. And the moment of inertia of these satellites is usually proportional to d to the power of 5. And whereas in the same time that the power budget of the satellite is usually proportional to the surface area of the satellites, then we can find that the power budget is usually proportional to d to the power of 2. That means that gives us an interesting insight that for the amount of torque that you require for the satellite, and also the amount of slew rate that you require for the satellite, that means how fast you are going to steer the satellite, that depends on two factors. For the torque, if you wanted to maintain the same angular acceleration for your smaller size of satellite and larger size of satellite, that means the required torque for your attitude actuators is going to be proportional to the moment of inertia. That means the torque you require is also proportional to d to the power of 5. And on the other hand, that's the maximum slew rate of your satellite depends on the maximum angular momentum you are able to put into the system divided by the moment of inertia of your satellites. So that also gives us an insight that if you wanted to maintain the same slew rate, for example, 3 degrees per second for your smaller CubeSats, and also the same slew rate for your larger small sats, to be also 3 degrees per second. That means when the satellite gets larger, the required angular momentum of your angular momentum exchanging cluster devices like reaction wheel or CMGs, its capability of storing storing angular momentum has to be proportional to the moment of inertia, and also that means it has to be proportional to d to the power of 5. So this gives us some very scary insight here is that whenever your satellite getting larger, that means the required capacity of your angular momentum exchanging device has to grow proportional to d to the power of 5, including its angular momentum capability and also its torque capability. However, the power available for you to input into your satellite, for example, you both reserve 20% of your power budget to the attitude actuators for a smaller or larger satellite, but you will find that it is getting closer and closer to its limitation, and your power budget is no longer sufficient for those power-hungry actuators for your satellite. That means when you are building larger satellites, you should look for devices they are able to provide you larger torque to power ratio or even larger angular momentum to power ratio or angular momentum density. So let's look into the potential candidate for our selection of the angular momentum exchanging devices. That includes the reaction wheels, which comes with a single axis configuration that it generates torque in its rotational axis by accelerating or decelerating the rotational speed of the reaction wheels. And on the other side, there comes to our control moment gyroscope, that it basically has a 2 degrees of freedom actuator rotor inside that is controlled to be spin in one single axis and to be controlled to do the tilting in the other axis. So we can see that the first axis of torque that is able to be generated by the CMG is the axis of its inner rotor axis. That you can still generate torque like you do for the reaction wheel. You accelerate or decelerate the rotational speed of the rotor and get torque in this axis. But on the second axis, we call the gyroscopic axis, that is generated by the rate of change of the angular momentum. That means when you're accelerating the rotor in this direction and you do the gimbal maneuver, you do the tilting, you can generate another direction of torque that we call the gyroscopic moment, that is proportional to the so-called the GT direction here, if you see the diagram that is plotted in the video here. And then that means these actuators are able to provide torque in two axes. Not all control moment gyroscope can do that, only for the CMGs that have variable speed capabilities that are able to create a reaction wheel torque in the inner rotor axis. But for those CMG that only has constant speed capability, that these inner rotor axis of the torque will vanish. So we can see one interesting behavior here is that the direction of the torque that is generated by reaction wheel is usually proportional to its angular velocity vector omega. So that means the mechanical power that is consumed by this reaction wheel has no way to be reduced or no way to be minimized. That it always consumes the largest mechanical power required. And however, for the control moment gyroscope, that it output torque in a more clever way. That's the GT direction of the torque, which is so-called the gyroscopic moment, is orthogonal to the direction of the angular velocity that is in the inner wheel axis. That means when these two vectors are nearly orthogonal to each other, then that means we get a minimum amount of the mechanical power. So usually, for example, for a 1 millinewton second of the reaction wheel, when it outputs its largest torque, it can go something up to 200 watts. However, for a CMG in the same size with also 1 Newton meter second of angular momentum, its power consumption can go no more than 15 watts or even less. So that is the beauty of utilizing gyroscopic torque with a clever device like a CMGs. About these principles behind, and then next we can look into how these characteristics are mapped into an actual use case scenario, as you can see from the plot here. That usually we will assume a trajectory for the satellite to do the maneuver back and forth in order to do a more objective analysis. That's picture a satellite like this, that it will do the steering in one single axis from the positive x to the positive z x, negative x, and go back and forth, go back and forth, go back and forth. So we can see that its slew angle is changing from its positive maximum to its negative minimum, and then it will experiences a angular acceleration processes, like you can see in the yellow line here, that it requires a torque for it to generate rate of change on its slew rate. And then when it reaches to its maximum slew rate, it will maintain a steady speed and let it float to the targeted orientation. And then when it reaches to the target slew angle, that it will generate another torque to stop it and then to rotate it back to the object that is in the opposite direction. So you can see that for satellite that is having larger moment of inertia, that its power consumption that is additional comparing to from the reaction wheel cluster comparing to the CMG cluster is getting larger and larger. Those reaction wheel is going to occupy more and more power budget from your satellite bus. And on the other hand, that if your slew angle is smaller, that means you are doing faster rate and smaller angle of the maneuvering of the satellite, then the power consumption that is generated by the reaction wheel will going to be larger as well, which means that the advantage of power for those CMG clusters is getting more and more obvious in those use case scenarios. Yep, so we talk about many advantages of these control moment gyroscope, but what are the downside for that? You can see that traditional reaction wheels, they are traditional control moment gyroscopes, they are mainly actuated by two motors. One motor that spin up the inner rotor axis, and the second motor that do the gimbal maneuver. So that means the traditional size of these CMGs are typically longer in its shape, and that will make its angular momentum density to be lower. And especially when you are placing the CMGs into a pyramid cluster and do a skew angle for those CMGs, it will occupy even more spaces over there. So that's why Tensor Tech developed this technology of spherical motor that is used to provide torque and drive the CMGs to spin up inside a spacecraft. So basically this technology utilizes only one single motor that we call spherical motor instead of multiple motors there. So it is able to shrink the size and make the form factor of the CMGs into a spherical shape. So that's when you are doing the tilting and or skewing angle of these CMGs, it will occupy extra space because it comes with a natural form factor of a spherical shape. And on the other hand, there are permanent magnets that is on top of this rotor, so that there is no slip ring required for you to conduct electrical currents into the inner wheel motors inside these gimbal. So that means no slip rings, so no wear out on these slip rings and no reliability concern for that. And in addition to that, when there's no slip ring, that means your steering law of CMG don't need to care about the number of gimbal maneuver over there, and then your steering law algorithm can mainly focusing on minimizing the power consumption for your CMG cluster. So that's these spherical motor design provides several advantages for the users that is looking for solutions that can boost the agility of the satellite in order to get higher revisit rates of their satellite constellation without the need to increase the number of their satellites. So let's get a peek into what's inside these CMG drive by spherical motor. You can see in the middle here is the rotor that contains permanent magnets that we invest resources to develop a magnetic field of it to optimize its performance. And also outside of that, there are coils that is manufactured in a specialized shape that can provide rotating magnetic field that surrounds the rotor to control it to spin and to steer in the three-dimensional space. Yep, so let's take a look into this control moment gyroscope. This one is our CMG1 that is designed for microsatellite and small satellite. So you can see that actually inside there is a gimbal. The gimbal inside that is contained with a gimbal axis that we already do a skew angle for you for that. So you can see that this form factor is still larger in terms of its volume comparing to reaction wheels in the same angular momentum storage capability. However, if you compare these CMG drive by spherical motor to CMGs drive by two single axis motor, you will find that its volume is much smaller comparing to the traditional CMGs. However, let's look into the real application scenario of the CMG, that when people put four of them into a pyramid cluster, that means these attitude actuators will need to have a skew angles to make the gimbal axis of their CMG or reaction wheels to have a differences in angle in relative to each other. So that's the total volume that is occupied by the traditional single gimbal CMGs is going to be much larger, up to close to 18 times r to the power of 3, where r is the dimension of the CMG. And these CMG drive by spherical motor doesn't occupy extra space due to the skew rotation of the CMG, because inside itself that it is a spherical shape. So when you tilt something in the spherical shape, its volume occupied doesn't increase. And when you compare it with a reaction wheel cluster, you will find its volume is actually even smaller than reaction wheel cluster, which is the amazing part of using this spherical motor technology in satellite constellations. Then let's get a detailed analysis into the amount of angular momentum that is able to be provided by these different kind of attitude actuators over here that is available for the user to choose from. And so you are able to give a better analysis for that. So let's see how does these angular momentum exchanging devices are arranged in space. You can see that usually they are placed in a pyramid configuration like this. So you can either have two actuators or even 4 actuators. So let's firstly see the case for reaction wheel. That when you put 4 reaction wheel that is into a pyramid cluster configuration, that they both have the same skew angle and form a pyramid cluster, you can see the angular momentum envelope that it generates can be around 1.5 Newton meter second of the radius for their angular momentum envelope, when they are using 4 identical reaction wheel that has each comes with a 1 Newton meter second of the angular momentum storage capability. However, if you are using CMG here, because the CMG has its natural capability of being able to steer the vector, the direction of their angular momentum vector, so that's when you have 4 CMGs and all these CMGs are steering the angular momentum vector into one single direction of the spacecraft, then you are able to put the angular momentum into only one single side of the satellite, so that can even give you a much larger angular momentum envelope dimensions here. Like for example here it can go up to 2.8 Newton meter second of the radius for the angular momentum envelope by just also using 1 Newton meter second of the control moment gyroscope. So it reveals something that actually CMGs are capable of having a much larger angular momentum density comparing to a reaction wheel cluster. And however, this is the case for constant speed CMG. And for the case of a variable speed CMG like this one that utilizing spherical motor technology, that's also the same case, that you have also the same dimension of the angular momentum envelope here for this pyramid cluster. And then also the additional advantage of these variable speed CMG is that it comes with singularity free characteristic, unlike the traditional constant speed CMG that will facing those something we call singularity surface. So not all command of the slew is permitted by the CMG cluster. But for the variable speed CMG, there is no limitation or the so-called singularity surface. So you are always able to steer your angular momentum vector into any direction in the 3-dimensional space, as long as the length of this angular momentum vector is within the radius of this angular momentum envelope. Then let's look into the advantage of the variable speed CMG. Another one that is its redundancy capability, that when you get 4 CMGs and then you fail up to 2, that you left only 2 variable speed CMG over there, you can see that it can still provide a valid angular momentum envelope, but just with smaller envelope radius. So you are still able to achieve 3-axis control, but just with a more smaller maximum slew rate from your spacecraft. However, that's not the case for constant speed CMG that only allow the user to do the gimbal maneuver control. When the 4 constant speed CMG fails with 2 of them, that you are not able to get a valid angular momentum envelope, so that you will end up having a angular momentum envelope that you are not able to achieve 3-axis attitude control. So that is a drawback of using these constant speed CMG, that it gives us less advantage in terms of reliability, because if using variable speed CMG that you are capable of controlling in 3 axis when you fail up to 2, even 2 CMGs. Yep, so this is a short introduction for you about these control moment gyroscope, the technology behind it, and the principles of it. So I hope you enjoyed, and then if you are willing and interested to see the further details about how CMG can be used in ADCS, please click my next video clips. Thank you.